Okay, thank you. This one maybe. Today I'm going to talk about the Tyre-Check. I'm interested in low-level Tyre-Check. But now I have added this guy, which means that I'm using a kind of solver to deal with infinite trace where we have some kind of recursion. So let's continue. Okay, which is my motivation? We have this guy, the Reduceron, which is a graph reduction machine that executes template code. Template code is basically, for those that are not familiar with it, is like byte code. So, oh, this other way around. Okay, we have this problem. If the template code or the low-level code is produced by some compiler, the best compiler in the history, we can provide some kind of type checking, for example, by type checking the high-level code. But if somebody, some bad guy, produces that code by hand, or that code is altered by some other source, can we guarantee that that code is type safe? Or probably we want to send, imagine that this is the code we send from here, and that is the producer, that is the consumer. We send this guy to here, and in the middle, somebody alters the code. Then, how can we guarantee that this is the same code that was in there? So, okay, there you go, minus month. As I said before, Miner is coming to the rescue, and our idea is to try to infer the type in this untyped template code. So, let me explain how this works. This is one way to produce template code, or compiled code. This is the source code, which is high-level code. Okay. So, in here, another thing that we are proposing is that we don't need any information in order to verify that this is accurate. So imagine that this part is produced in York, and this is executed in some other country. And before we run this guy, we can check if that guy is the guy who is coming from Europe. So here this is important to say that this is not dynamic checking, it's static checking. This is at log time. This is one step before the run of the. So this is a good problem, because we need a way to provide a fast type checking queue. This should be a small guy, and it should be fast, and it should be the best of the best. So Then, if we want to provide some information here, this type information or annotation should be small. So that is another story that I think. So this is the Haskell data representation of the template code, which means a program is a list of templates, and every template is a function definition, which consists of an additive, an application, and a list of applications. This application is a list of atoms, and here we have every single atom. This is for numerical values. This is functions. The array to the function and the index of the function in the template in this list. The arguments of the function. This is the primitive plus and something. This is the constructor for data type. This is the array to the constructor and the index of the constructor. So we can see this guy as this is the like let expressions. This should be this is the body of the expression, and this list of applications is the bindings. So in here in blue we have these two guys. This is obvious. This is a pointer. A pointer from here to one application here or complete other application. And also we have this funny thing which is a tab. This is basically to handle the way how the Reduceron works with the case expression. This is the okay. I will start for the last. This is the number of free variables. I will use it like this. This is the number of alternatives. And this is the starting point in the list of the results here. So let's see. For example, this is the code in FLight. FLight basically is a code. Is the core language for Haskell. And the funny thing in here is that we produce or calculate the length of the list by using this. And the only difference with the standard length is that we return this natural number. So this is the first step, and at some point in the compilation, we have, or the compiler, have this kind of transformations which translate this case expression into this list of definition. It's like something like confirmation plus initialize, something like that. And this is a table which is defined here. And this is the actual code that I'm trying to verify. If you see, you don't have type information here. This is the, you can see this as this guy. And these other two templates are the alternative. This is the constructor for this guy. From here to there is the right hand side. And here we have this recursive code. This is the function number of 0, which has one pattern. So in this slide, I will explain very fast how this. This is the outside definition, which includes type functions and classic variables. But in here, because of the nature of how the operational semantics works in template code, this is for primitives. For example, ani is this guy, and this is type equivalent. Ani is a function from this we can see this as an additive, for example, print 2 or print 1, and this is a type. And also ani, I mean, once we reduce this guy, we got this other type. So basically, this is equivalent. And that guy is to deal with tables, the tab constructor. So this is a table which is a list of vector these guys, and this is the index of the alternative, which binds to type. So this can be empty. So what is the relation of why we want to use recursive equations? So I don't know French, but I think it's Colin. He proposes one paper called products and another way to solve equations. This is basically used in Polo, in which the term graphs are represented as a set of equations, and it has some nice properties, like, for example, the 3 solutions minima, which is good for us because if we infer the types and we send that information from one part to another part, so that should be minimum. And he proposes that is a good way to deal with the recursion on terms. So I don't remember which talk was, I think was the third one. So this is one application. So you remember Cardelli in one paper or basic polymorphism something, he states in there that we can see the type inference problem as solving a set of equations or following the classical way. So in our case, we make this in 2 stages. The first one is collect equations, and the other one is solve that equations. So this is the way we are trying to solve this problem. This is the length nav function. This is the case expressing the one. Don't worry about that. This is just the main function. And then the first step is to collect the equations. If I'm not wrong, that is the correct set of equations for that type. For example, these 2 guys, L and M, are the types of these 2. This is for the last. M is for the last. This is the index number 1, index number 1. Index number 0 is this guy. And this part is some tricky part that we infer from this additive. So basically this is the right hand side. If you see this L is in here, and is in here. But in here we don't have any information or any recursive code. So inspecting the code in here, we can obtain that information. also by using this constructor. We have a constructor in here, and also we have this guy. We can infer some analysis that is a recursive code. So we have these two equations, which makes this guy E and O to C. And then we pass to the solver. And this guy, F1, is the type of this. So basically, it's a function of one argument to some type B, where the type D is recursive. This is the type of the argument, and this is the type of the result type, and this is the recursive code here. So this is the type of NAT, and this is the type of list. The first component of the list, this is the constructor, the classic constructor, and this can be seen as the nil. This is the successor, and this is the 0. And here we can have a lot more variables in there. So one funny thing in here is that we need to distinguish in here which variables are polymorphic. For example, this is P is polymorphic. I'm sorry, this is the recursive variable, and this is the polymorphic variable. And these target variables are just locally quantified. So this is our way to hide this information. So how can I be sure that this Tyre-Check-I is working? So one way is to provide a proof that it is sound, but my approach is more, I don't remember the word, but it's more practical. So I used to test this Tyre-Check-I by mutating the code. We have a valid template code and then mutate them. So that is the idea. In here, we have the set of mutations in this universe, and this set is the OK sets, which is the sets of well-behaved programs. This is the operational semantics, and this is the set of type inference programs, which is the web type programs. So we discriminate these guys. I mean, this is the dev code. We use a conservative analysis to discriminate this dev code. That is because that is the reason why we do this, because it's a conservative. And also we have some kind of analysis for non-termination. So we're interested in this part and in these two guys. We want to keep as minimal as possible these guys. This is the good programs, the well-behaved programs that doesn't Tyre-Check, and these are the bad behaved programs that we can have applied. So that's quite fun. And this is this is the result for one single mutation for the previous example. We got this number of mutations, and over here there are a lot of mutations that we checked before for some kind of sanity analysis. And we got this guy. We don't have dead code and non-termination, and we have 5 good guys that are stopped by Tyre-Check-I, and we have 8 bad programs that are our Tyre-Check-I. So basically, most of the programs, or according to my experiments, are related with the allocation function. So one way to be with that is probably is to add some kind of added information. I mean that information can be passed from the high level specification to the low level. Some related work is the proof problem code by Nebula, type of assembly language. This work is they include some annotations of some proofs. We are not dealing now with proofs. More recently, this is more oriented to dependent types. This, according to my reading, this is oriented to dependent types, and this is based on type of assembly. So conclusions, I think it's possible to build a Tyre-Check-I even if we don't have enough information. We don't require any extra information for now. Probably we have cheating here because this is the actual constructor in the paper, in the original paper. It only has one. And we use another. We have provided for primitives and means some kind of functional types depending on the number of the arguments. And of course, we want to use this kind of three solutions to represent all that. Future work and improve by annotations and test more programs. I want to keep focusing this guy. And I want to check components, probably one template for a couple of components. So that's it. Thank you.
Yeah, in the interest of an on-time lunch, if you have a burning question, a quick one, you can ask us. Otherwise, I would suggest we discuss it over lunch. Any questions? And let's thank the speaker again and move on.